I just have a question. Okay, so for this one,
Okay, so we did start talking about this last time, a very brief bit, because we wanted to talk about our project a little bit more, but we talked about how people try to sell you things and they try to make them look a lot better than they actually are. And so we had some statements that they said, I can't reveal these details yet, but you will love this product. It will improve your life in more ways than you can count. Its only downside is that it will eventually kill everyone who uses it. Will you buy this one? Well, no, because we know the end result would be death. Now, we do know that there are people who um, become addicted to drugs when they may physically know that that's going to lead to death, but they would not knowingly choose that if they're like, I just want to die, right? No one was buying, so we've made some improvements. Your chance of being killed by the product is now only 1 in 10. Ready to buy? Well, I don't want to be that 1 in 10, and most people wouldn't either. Okay, so this time we've really perfected it. We made it so safe that it would take about 20 years for it to kill as many Americans as live in San Francisco, though admittedly it will injure another 4 million each year. Still, you'll love it, and it can be yours for only $30,000. So, and we've all heard these advertising ploys. Now, these are a little bit dramatic. Most of the time, if it was going to kill you, they definitely wouldn't tell you. They would try to hide that from you. And so we have some perceptions about things, and sometimes that plays into what we think is going to happen. And when we think about, we talked about this very briefly last time, but when we think about a terrorist attack can be pretty scary because of a couple of things. Most of the time, a terrorist attack is something that's going to kill a large amount of people at one time. So like when we think about 9/11, that's most Americans think about a terrorist attack. That killed a lot of people at one time. And it's also something that's in the news. The news is not going to, so if we compare these three things, the news is going to probably report every terrorist attack that happens in the United States. They're not going to report every car crash, and they're not going to report every injury by firearms. Okay, so this terrorist attack thing is in our psyche as being a huge deal. And so when we look at these and say, which situation are you more likely to die in? Okay, some people don't think about car crashes and firearms as much because it's not in their face, and maybe it's not as scary to them. Now, if you travel a lot, last time we said we think maybe it would be car crash because we see a lot of those. Okay, so when we look at this terrorist attack and we look at these years, we're just looking at 1975 through 2015. Well, the reality of the situation is there's 3,432 U.S. murders in those years that dealt with terrorist attacks. Okay, and if we divided that out by how many happened per year, that's going to give us about 85 a year. And I had said 85 a day, and I was like, there's no way that would average out to that because we got about a 30-year span. So then if we take into account 9/11, so if we subtract off the deaths from 9/11, because that was a huge thing that happened that happened in one day, 9/11, there were 2,983 murders just on 9/11. So if we subtract those off, then we would end up with a little over 1,000, which would lead us to 11 per year. Well, that's not a lot when you think about 11 deaths per year. If we just take off 9/11, if we kept 9/11, it would be 85 per year. But that kind of thing just doesn't happen a lot in the United States. So this 85 per year would kind of be like an outlier. The 11 per year without the 9/11 would be more realistic. Okay, and the reality is that if the car crashes happen 4,000 times as much, and that deaths by firearms happen 3,000 times as much. So car crash and firearms are way more deadly to us than terrorist attacks. But because that terrorist attack has that, it's in the media, it's in the news, it's in all that stuff, sometimes it's a little bit larger than life. And that's why we sometimes have this big perception that we're scared of all this stuff. Okay, so, and the media can play a big role into creating that hysteria. They do it a lot with the coronavirus right now, and I'm not trying to be ugly about that, but they don't report the entirety of the information. For example, one of the statistics is, yeah, we've had a lot of people die from coronavirus, but we've also had a major amount of those people that died of coronavirus had two other comorbidities, which means that they were dying anyway. So if you take that into account, they withhold whatever information that they can to create hysteria sometimes. But we're more fearful of a situation in which there is a lack of control, okay? So that's just natural. If we're not able to control the situation, it's a lot more scary. The potential to harm to a large number of people at once. That's one of the reasons why the whole terrorist attack thing is scary, because I mean, we don't know. They could come in and do something to a whole bunch of people at once, and we have no control over that situation. The news media makes them more available to our mind than other everyday threats. So when we're looking at this stuff, it's at the forefront of our mind because it's being reported. So a lot of times data is reported in different ways. So they've got travel risks down here. We could report this per 100,000 people. And a lot of times when we're talking about statistics, that's exactly what happens. We report for 100,000 people because there's so many people that if we reported for every single person, it would be a huge number. Sometimes we might report it per trip or per mile that the person's traveled. So we've got this chart, and it says the chart below shows the number of automobile fatalities and the total number of vehicle miles driven among all Americans for each year over a period of more than 4 decades. In terms of the death rate per 100 million vehicles driven, and this is important right here, per 100 million vehicle miles driven. The death rate is being given per 100 million vehicle miles driven. Okay. How has the risk of driving changed over this period? Is driving safer? Let me, I'm going to make this just a bit bigger. First thing you want to do is you want to look at your chart, okay, because there's a lot of things kind of going on this chart, and the one that you all have copies of is a little bit dark. But on this side, we've got deaths, right? It looks like it's 10,000, 20,000, 30,000, 40,000. On this right side, we've got vehicle miles in millions that are driven. So this 0.6 right here means 0.6 million vehicle miles driven. Okay, this 1.2 is million miles driven, 1.8 million vehicle miles driven. So those aren't just like 2 miles, 3 miles. Those are millions of miles driven. So we've got two things going on. We got deaths on this side, and we've got vehicle miles driven on this side in millions. And then when you look at the bottom, you've got years. Okay, and then it tells us that these bars represent the number of deaths, and that the line, you can kind of see the line going through here, represents the vehicle miles driven that's talking about this right axis. Okay, so let's look at 1970. So in 1970, what did we have happen? We have 52,000 deaths and divided by 1.1 times 10 to the 12th miles. Okay. So where am I coming up with this stuff from? Here's 1970, right here. The first number. When you go up to the top of the line on 1970, you had to kind of approximate because it didn't tell us it was exactly 52,000, but it was a little bit above 50,000. So we've approximated 52,000. And then we've got 1.1 times 10 to the 12th. Okay, so this is kind of hard for me to do on here, but if you draw a straight line, here's where we're at in 1970. We draw a straight line, except for I can't draw a straight line, but if I draw a straight line on that, because we're going off our line graph here, it looks like it's going to come under right underneath (1.2). So that's where they're coming up with 1.1. Okay, and then times 10 to the 12th is coming from the part where we're talking about million miles. So times 10 to the 12th. And we've got to get rid of that. So we're going to say 10 to the 8th miles over 100 million miles. And when we do that calculation, it ends up being about 4.7 deaths per 100 million miles. Okay, let's look at what happens in 2016. I'll drop down to 2016. In 2016, which is way down here, if we look at this bar that's right here and we follow it over, it looks like it's a little bit underneath 40,000. Okay, 2016, it's gonna be just a little bit underneath 40,000. The book says 37,000, so I'm gonna use their estimate. And if we look at our line at 2016, it's way up here. It's way up here, so they're saying approximately 3.2 times 10 to the 12th miles. We know that this is every 100,000, a million miles, 100 million miles, sorry. So we've got to get that to cancel out. So they're just using a conversion to get that 100 million miles canceled out. And that's going to give us about 1.2 deaths per 100 million miles. Okay. So, what's the explanation for that? We've gotten safer, right? Something's happened. We've gotten safer over the years. We don't have as many deaths per million of miles driven. And it does matter how, if you don't ever drive in a car, you don't have to drive a long ways, you're less likely to have an accident. So it does matter if you're driving a lot or a little bit. But our cars have gotten safer. our roads have probably gotten safer as far as how that they are built and designed. So those are some of the things that probably contributed to that. That I didn't think about that, but that's true. The seatbelt requirement is probably decreased. Yeah, you're exactly right. Because I remember my parents telling me that, yeah, that y'all just used to stand up back there in the back seat or be flopping around. Yeah, that's probably definitely changed a lot. So this next thing says for the 5-year period, 2012 to 2016, U.S. commercial airlines flew about 8 billion miles per year and had only a total of 5 crash-related fatalities, or an average mean of 1 death per year. Use these numbers to calculate the date. I think it's supposed to say death. Sorry. Death rate per mile of air travel. Compare the risk of flying to the risk of driving. And we already know, right? What do we know? We think it's the flying's going to have a bigger risk or less risk. My daughter is scared to death. My oldest daughter is scared to death of flying. And I tell her this fact over and over again, that the chances of you dying in a plane is way, way, way less than you dying in a car. But you can tell somebody, and that's where that fear of things like the terrorist attacks and all that takes over. You can't rationalize anymore because their fear is not out of, it's a little bit not real, right? So we're going to do 1 death divided by 8 times 10 to the 9th. Why 8 times 10 to the 9th? It said there were 8 billion, we got 8 billion miles per year. If you wrote the number, this would be the same thing. You don't have to write 8 times 10 to the 9th, but if you did billions, it would be dividing by 8 with 9 zeros behind it. So that's why it's 8 times 10 to the 9th. If you typed in 8 billion just like this and didn't do 8 times 10 to the 9th, you would still get the right answer. It would be perfectly fine. This comes up as 1.25 times 10 to the negative 10th. Okay, well, what is that number? That's death per mile. I mean, if we know scientific notation means you're going to move your decimal. If it's a negative 10, we're going to move it back 10 places. So we put our decimal here, and all this in front would have zeros. So 0.000000000125% chance of dying per mile flown, which is crazy low. If we were to multiply that by 100 and get a percent, that would take away 2 of the zeros, so it would be 0.00. What? 1, 2, 3, 4, 5, 6, 7. Yeah, 125% chance of dying. So very, very, very low, right? Okay. So a lot of companies use vital statistics whenever they are making predictions. Insurance companies are one of the number one things that they're going to use statistics to help them make or lose money, right? Hopefully they're not using it to help them lose money, but they want to use statistics to access risk and set rates. Okay, insurance companies use vital statistics to access risk and set rates. I think whenever one of the most dangerous jobs, they say in Arkansas, is to be a crop duster. Those are like the people who on farms, they have those planes, you know, and the planes come in and they spray the crops with the, what do you call that? It's not fertilizer, but it kills the bugs, right? Pesticides. So that's one of the most dangerous jobs. So if an insurance company wants to know what your job is and you tell them that, your life insurance is going to be crazy high because they use those vital statistics to make predictions on what they should charge. Okay. Another example is the state of Arkansas has their teachers have a different insurance group than the rest of their state because there are a lot of teachers who stay teaching for a long time. And that, so when you look at school districts, a lot of times they still have a lot of staff that is older. And so that drives that teacher's insurance price up. So they want to keep them in a separate group so that they can make those people pay more. And they don't want to put them in the group with the rest of the people because that would jack their prices up. So insurance companies are one of the number one things. What happens when you start reaching a certain age and you want life insurance? Well, they're going to say, well, if you're in the ages of 40 to 45, your insurance is going to be this. But now that you're 50 to 55, it starts getting more expensive and more expensive because the risk of your death is going up. So they don't want to, they know this and they don't want to, they build that into their cost, right? Health profession is also one to, they use it to assess medical progress. This is kind of sad, but not kind of sad, it is sad. Health profession use them a whole lot, statistics, because to help them make decisions. Okay, and so this could be a good thing. I mean, I said it was sad. It could be a good thing or it could be a bad thing. But if you're somebody who has a very rare disease and you want a treatment, so I put assess medical progress and decide where research resources should be concentrated. That is kind of hard to read. So if you've got a very rare disease and you would like it to be looked at, chances are you're at the end of the totem pole because they want to be able to help as many people as possible. So those rare diseases would get less money for research than the ones that were going to help a lot of people. So those very rare cancers are going to be at the end versus the ones that are more common. Heart disease and things like that are going to be researched more than something that is not as prominent, I guess, because a couple of reasons, right? If you don't have anybody to pay, this is the backside of it, the mean kind of side of it. But if there's not very many people that have that disease, then there's not going to be that many people that pay for the treatment, right? If you got a whole bunch of people that have the disease, and they're going to make money off of finding the cure to this treatment and then giving it. So, demographers, they use birth and death rates to predict future trends. And we're going to come back to that at the end of this class, but okay, they look at birth rates and death rates to predict future trends. And that's not just important for healthcare, that's important for businesses, that's important for us as a college. They actually say that there were a lot less people born in y'all's section. So I think there's about 10 years where we're supposed to have a decline in college tuition because there's going to be less people coming to college. So we'll have to adjust to that. So those birth rates and those death rates are important. Okay, example 3. This says, assuming a U.S. population of 315 million, find and interpret risk per person for 100,000 people. Here this is again. You're going to need to pay attention to that because when it says for 100,000 per people, you know you're not doing it for every one person. So that kind of plays into this. For accidents and suicide. So let's look at what happened if we compare this accidents and crashes. Okay, so I'm just looking at my table here and it says accidents is 122,000 and where are we getting the I don't know why that says that. It's different than in here. So we'll just do what we have here then, which is not a big deal. So on this table, it says this table is different than what the book says. We've got 122,800 accidents, and that would be including car crashes. Okay, and in the United States, I'm just getting this from, it says that there's a population up here in the United States of 315 million people, so I would use that number. I'm sure that that's changed a little bit. Okay, and we would divide that. So the other thing, this is for 100,000 people, which is important. We'll do that in the end. Let's just, so 122,000 divide 800 divided by 315 million. This is getting me, I'm going to round a little bit, 3.898 times 10 to the negative 4th power is what's popping up on my screen. And that's going to be the number of deaths per person. Okay, if I want to, we convert these numbers to deaths per 100,000 people by multiplying their per rates by 100,000. So I would need to come back and say, okay, if we want to know what the times 100,000 death rate is, or per 100,000 people, we would multiply by 100,000, which is going to make it a little bit easy. See, to me, this number right here is hard to talk about because it's so small. So this number is 38.984 deaths per 100,000 people. So if we've got 100,000 people, approximately or if we round it up, 39 people of them are going to die from accident or car crashes. Compared to cancer, which is on this table, 575,300. So we still have 315 million people that we're talking about in the United States. Okay. This is getting me approximately 0.0018. And if that's death per person, that's really still kind of hard for me to talk about. So I'm going to multiply it by my 100,000. $182.63 And that would be our deaths per 100,000. So you can see that you would be more likely to die of cancer than a car crash. That puts it in perspective. So kind of crazy. Because I would think, you know, so many people travel, you think, man, there'd be more people that would die of a car crash than there would be of cancer. But according to these causes of death, that cancer diagnosis is more. Okay. The probability of death from a heart rate is, or heart disease is much higher than the probability of death rate by accident, but these data include all age groups. Okay, so once again, this includes every single age group. How do you think the risk of death from heart disease or from an accident differ between young people and old people? So let's just make a table. We're not going to talk about this a long time, but that table included everybody, not heart rate, heart disease. Okay, we'll make this really short and simple. But older people, I mean, don't you think they have a higher chance of dying of heart? They got a higher chance of dying from heart disease than younger people. And younger people have a higher chance of dying in a car crash than they do heart disease, right? And older people, to be honest with you, if they're at the age where they're starting to get heart disease, they don't travel a lot. So their car crash rate is probably a little bit lower. Okay, and this is one of the things I was going back to talking about, all that data on the coronavirus. Okay, so I don't have the answer, and I'm not proclaiming that I do, but I do think that the numbers are very misleading because there's other things that have to do with coronavirus death besides coronavirus. Like, what else was wrong with that person? Okay. I mean, they're saying that one of the statistics did say that that only about 5% of the deaths from coronavirus were not related to anything else. The other 95%, those people had two other comorbidities, which could have been pneumonia, or they could have had heart disease, things that were going to cause them to die anyway. So you just have to be careful about what statistics you believe and make sure that you think the process through. Like, could anything else have affected that, or is it just based on this? Because you can really make numbers say anything you want them to. I mean, you can modify the wording to make them fit your agenda, which is unfortunate. Okay, so very close to being done with this. Here are a couple of tables about life expectancy. Okay, this says life expectancy is the number of additional years a person of a given age today can expect to live on average, often used to compare overall health at different times or in different countries. So we've got this one chart that kind of looks like, and we're going to talk about this next class, but it looks a little bit exponential, which means it starts really small and it gets really, really big, really, really fast, grows really fast. This one is a little bit more linear. It does have a little bit of a curve, but it starts high and then it gets pretty low and then it kind of slows down a little bit. So this is deaths per 1,000 people. This is US death rate age 0 to 80, and this is their age. Okay, so if you look at 60 right here, if you look at 60 and then you kind of go over to this line, follow it over, it looks like that deaths per 1,000 people, there's about 8. So if you're 60, you got about 8 out of 1,000 people chance that you're going to die this year. Okay, if you get up to about 80 though, got 45 out of 1,000 people that you're going to die this year, and it just goes up and up, right? Okay, this chart's a little bit different. It says U.S. life expectancy between age 0 to 100. You got your age down here and you got your years over here. Two different things. This is talking about years and age. So if you're 20, and you follow this over, it says 60. What that means is if you're 20, you can expect to live about 60 more years. This one, if you're 50, if you follow it over, it looks like we're a little over 30 more years. If you're 90, looks like if you follow this over, you're about 5 more years. Okay, so that they work different. Two different graphs. I mean, you just have to read what they're saying. So life expectancy is the number of additional years a person of a given age can expect to live on average. Life expectancy at birth is the life expectancy for a newborn infant. It says, what is the life expectancy of an American? Okay. And I got this. This may be not very current. I mean, it's current in that last 5 years. It's not old, but what's the life expectancy of an American man? 76. What's the life expectancy of an American woman? 81. Okay. American man does not live as long as an American woman usually. Because we're awesome. Just joking. Because they can't multitask. Just joking. Not really. Okay. So use the figures shown, find the life expectancies of a 20-year-old person and a 60-year-old person. And we kind of already went over this a little bit, but we're going to do this real quick. So on this graph, if we want the life expectancy of a 20-year-old person, we would go to 20. And then we would go over, and it looks like the 20-year-old is going to live 60 more years. And if we wanted to find the life expectancy of, what's the other one want? They want 60, a 60-year-old. We would go to 60, and then we would go over. And it might just be a little bit above 20, but I'm getting around 20 more years. Which, if you'll notice, they both add up to about 80. All right, so if you're 20, you're supposed to live about 60 years. If you're 60, you got about 20 more years. Figure 5 says, using the figure determine how much life expectancies rose during the 20th century. Suppose that life expectancies rise by the same amount during this century. What will life expectancies at birth be for children born in 2100, the year 2100? What are the implications to your own life expectancy? Explain. Okay. So for women, life expectancy rose from about 48 years in 1900 to 80 years in 2000. So where are we getting this from? It's just, I'm going to change this to blue because the line for the woman is blue. So in 1900, we're about right here. We're about 48 years in 1900. In the year 2000, so if we follow 2000 up, we are right in here, which looks like at 80. So if you look at the difference between those, 80 minus 48, it's 32 years. Over that 100-year period from 1900 to 2000, women have added 32 years life expectancy on theirs. Okay, let's look at men. Men are the red line. In 1900, men were about, they're down here. They're saying about 46. And you do have to kind of estimate those. In 2000, though, men, $74 years. So 74 minus 46 is going to be 28 years. So men haven't done that bad for themselves either, right? They've added 28 years of life expectancy in 100 years. So what does that mean in 2100? The year 2100 was what this question was asking. So in 2100, for women, okay, right now, women are living to be 80. So if you add on that 32 years, that means that we would live to be 112 years old in 2100. Men right now live to be 74. And if you add on their 28 years, they're going to be about 102 years old, their life expectancy. Now, how realistic is this? Because you also have to use your brain, right? I mean, back in 1900, what was the issue with life expectancy? I mean, why are people dying so early? Lack of medical care, lack of medicine in general, right? I mean, people there was no x-ray machine. There was no, like all this current modern technology that we have that help us to save people's lives. There was a lot of the discoveries in medicine weren't there. If you needed a doctor, there was no ambulance. The transportation system was terrible. You weren't going to be able to, you had to call. I don't know if y'all ever watched Little House on the Prairie, but that used to be one of my favorite shows when I was a little girl. But you had to call Doc, and it might be 12 hours before he could get there on his horse and buggy. I mean, so these people didn't have a lot of medical care, and it's definitely changed. The problem with this 32, I think we probably will increase our life expectancy some. I do not think it will be 32 and 28 years, because we can keep on increasing our medical technology, but I don't see, and I'm not saying we can't, but there's going to be a cap on that, right? I mean, eventually everybody passes away, and we can keep trying to live longer and longer and longer. But there was this big jump because we were able to make strides in transportation and medical care and all those things. And I don't know that we're going to be able to keep up at that pace. We can add on some more. I'm not trying to be a pessimist, but okay. It's possible, I guess. I just don't think that we'll do that. Last thing. This says, because of the changing, I said we were going to go back to this question. And when we got up here, we were talking about, really quick, we were talking about demographers and how they look at death rates and birth rates to predict trends. Well, this is one of the things that we've been kind of worried about in America. But it says, because of the changing age makeup of the U.S. population, the number of retirees qualifying for Social Security benefits is expected to become larger in the future, while the number of wage earners paying Social Security taxes is expected to grow much more slowly for a couple of reasons. We had a baby boom, okay, and I know you probably heard about that, where people were having a lot of babies. And now we don't have that as much. People are starting to have your typical nuclear family, which would they say your girl and your boy, and that they just stay with two kids. So when we're reducing our population size, there's not going to be enough to pay for these people who are retiring. It says, as a result, one of the biggest challenges to the future Social Security is finding a way to make sure there's enough money to pay for benefits for future retirees. Any estimate of future Social Security costs depends on assumptions about how long people will live, because unless there are corresponding change in retirees' age, which is what we just got through talking about. What the other thing that's happening to these retirees is they are living longer now because we have good medical care. Longer lifespans result in more years collecting these benefits. Unfortunately, these assumptions are difficult to make with confidence. For example, recent projections by Social Security officials have assumed that life expectancy at birth will rise only slightly during the rest of the century. However, as discussed in example 5, it seems reasonable to imagine life expectancy might increase by a fairly large amount. If that turns out to be the case, it will be greater for public health, but will greatly exacerbate the budgetary problems facing Social Security and Medicare. So when we're looking at this and when the insurance companies are looking at retirement and all that kind of stuff, they have to take into account, okay, we got this much coming in, but we got a whole lot more going out. And I don't know that I have the answer to the problem, but somebody's going to have to pay for it, right? And it seems to me like it's going to be the younger population is going to have to end up paying more for Social Security to cover all the older people right now, or we won't get any, right? So that is one of that's just something for you to think about. This is all these projections that they're making with statistics. This is one problem that's a real world problem that we got to deal with. Okay, that's the end of section 7D.